A fast food chain claims that the mean time to order food at their restaurant is 60 seconds with a standard deviation of 30 seconds. You decide to put this claim to the test and go to one of the restaurants to observe actual wait times. You took a sample of 36 customers and find that the mean order time was 75 seconds. Does this finding provide enough evidence to contradict the fast food chain's claim of service? Okay, follow the 5 steps shown below in the previous lesson and use alpha as 0.5. Okay, so state your null and alternative hypothesis. The null hypothesis is that the restaurant is telling the truth, that it is in fact, the null hypothesis, like James said, is always like, we assume that, the status quo is in effect, and, we have no reason to doubt that things are the way that, other than what they appear to be. So, here the null is that, no, the order time is less than or equal to 60 seconds, which is what they say. But then our alternative hypothesis is, well, no, it's actually higher than what they're saying. And now we're going to see, well, what are the odds of observing, because we took a sample and we calculated the mean, and that mean came out to be 75 seconds, right? But that could just be the result of random chance where we happened to pick a sample, where that led to a higher average. But if we were to take enough samples over enough of a time space, the mean would in fact come out to 60 seconds. So we want to test, well, what's the idea that what's the probability that we would in fact pick a sample where the mean was 75 seconds, given that the true mean is in fact 60 seconds. So to do that, we're going to do import math.scipy, import scipy.stats. Mu is equal to 60. Mu, as we all know, is the population mean, right? Sigma is equal to 30. Sigma is the population standard deviation, and it has been given to us in this case, so we have that to go on. N is equal to 36, right? N is equal to, that's the number of people in our sample. Sure enough, yeah, that's 36 customers. X bar is equal to 75. X bar, remember, is the mean of the sample that we pulled, right? As opposed to the mu, which is the population. So the z-score here is going to be x bar minus mu over sigma divided by math square root n. Why we're using that is because that's the formula that we use. We'll let that load. We'll get back to it. So we get the z-score, right? And the z-score is going to tell us, x bar, that's the mean that we observed, okay? Subtract that from the population mean, and then divide by, the standard deviation divided by the square root of the sample size. And that'll tell us, well, that observation is that many standard deviations away from the population mean. So the z is now telling us that the 75-second score is, whatever number of standard deviations away. Well, it says it down here, p comma z. So z is 3, right? So what that means is that the 75-second set mean is 3 standard deviations away from the population mean of 60. And from what we remember, that if you go 3 standard deviations out, that means that less than, I think, 5% of, or even less than that, it's a large number of standard deviations. So very few observations will fall outside of 3 standard deviations, given that, the population mean is 60. And then P is equal to 1 minus stats.norm.cdf, right? And what is that doing? Anyone? Bueller?
I'm trying to remember what the name of the definition is for that, and I'm drawing a blank. The t-score, right?
No,
no,
we're not at the t-score.
1 minus.
That signifies how significant the sample is, right? Like if I remember when we were looking at p-scores before, if it's really high, it's got a correlation with something else.
Okay.
Yes, it's the probability, right?
Yes, it's
it's the alpha.
No.
Essentially.
Okay, so stats.norm, okay, the CDF, let's go back to what the CDF was. That's the cumulative density function.
Oh, that's right.
That's that S-shaped curve.
Remember
that S-shaped curve?
Right.
And what that does is it tells you, when you give it an X, it'll say, well, up till X, we've observed this many of the values. So it tells you, what's the probability of finding a value that is at least as big as X, but could be less. right?
Got it.
It accumulates.
Right.
So in the CDF, when we pass in Z, this function will return to us, it'll tell us that the odds of observing a value that is as big as or less than this Z-score. And we're going to subtract that from 1 because we want to see, well, you know, how many values are less than because, okay.
Because, well, if you have a normalized function, they all add up to 1, right?
They all
so
add
you're
up,
subtracting, right? So that
right, because you want to find the probability that we would find a value that is at least as small as Z, right? It could be more than Z, but it has to be at least Z because that is what we observed in our sample, right? So that's why we subtract from 1 because that says, okay, the best way to do it is to actually look at the curve, right? There you go, okay? That's what that tells us because we want to find this area, right? The one that's shaded in blue, right? That's the probability we're interested in because that tells us, well, that's the probability that we could have observed a value, we could have pulled a sample and observed a sample mean, given that the population mean is, well, 0 because this is a standard, right? Because so that's what we want. That's why we subtracted from 1 because all the area under this curve adds up to 1 because that's the probability. That's like, you know, all the probability of observing any sample mean. We want to know, well, what are the odds that we would observe a sample mean that is at least as big as 75? It could be bigger, right? But it has to be at least 75. So, and the only samples where the mean is at least 75 is right at the tail end right there, right here. And that's why we subtract from 1, because that'll give us this probability. CDF will tell us this area, right? The cumulative density function tells us, you know, how many means are at least are less than or equal to the sample mean, because it keeps adding on, right? It says that, like, you know, if we pulled 100 samples, you know, 95 of them would be less than 75. By the time we get to 3 standard deviations out, we have observed 95 or 99% of possible sample means that we could have seen, you know, and then anything that big or larger, the odds are that much. And that's what CDF does. Hang on, I really want to show you guys the all right, let's go back and just for a second, let's just look at the cumulative distribution. That's going to be good, trust me. Right. So that's our the probability density function, right? That tells us, you know, what are the odds of a given value. But then to find the odds of a range of values, we would have to find the area under 2 values. So instead of that, we use the CDF, and that really leads us to this curve. And then on this curve, all we have to do is we want to see, well, what are the odds that we would see a value that is at least is less than 85, and we just look at what the y value is here, and then that y value just tells us that of all of our observations, you know, 0.8 or 0.85% or 0.85 of them or 85% of them are going to be less than 85, and that's what CDF is doing.
I'm glad you went over that again.
Yeah. Okay. So that gives us our p-value, and that's our p-value, is the probability, and that comes down here. So the probability is 0.01, which is minuscule. It's like, I think that's not even 1%. That's like 0.1% chance that we would observe a sample mean of 75 if what they're saying is true, that the actual population mean is 60 seconds. So what I'm saying is, you know, hey, I did my own sample and I saw the mean was 75%. And if you guys are right that the average across all of your restaurants is in fact 60, then the chances that I would have seen a sample where the mean was 75 is 0.1%, which is highly unlikely that I would have drawn a sample of that means. So what that tells us is that your actual population mean is not 60, it's probably something higher than that. And you guys are inflating your numbers to do better business or something. Make sense?
Yep.
Cool. Keep moving. All right. 25 students complete a preparation program for taking the SAT test. Here are the SAT scores from the 25 students who completed the program. All right, that's the scores. We know that the population average for SAT scores is 500 with a standard deviation of 100. Hang on, guys. 1 second. Okay. All right, so we have all of those. We know that, okay. So now we have our 25 students SAT score significantly higher than the population's mean score, right? So what is our null hypothesis? I'm gonna scroll up so you guys can read it.
The null hypothesis that it isn't higher.
That our students, their average SAT score is not higher, that they're not special, they're the same as everybody else, and their average is going to be the same as the general population of everybody who takes the SAT score. The alternative hypothesis is that no, our group of 25 students, they are in fact special, they have a distinction from the population, and because they took that course, their average will be higher. And the fact that their average is higher is not the probability of random chance, that there is in fact, the course that they took did in fact have some effect on them, or rather that it's highly likely that that course had that effect on them, because the chances that any random group of 25 people would have an average that much higher than what the population is so low that we are led to conclude that yes, the course did in fact have a beneficial effect in raising their average SAT score. So let's walk through it. Okay, so the alternative is that there is an increase in grades. The null is that there's no increase in grades. Simple enough, we're going to pop all of their scores into an array. We have that up there. We're going to paste it. X bar, the sample mean, is now simply x dot mean, the mean of that array. N is the length of x, which is just the number of members and a number of individual units in the sample that we drew. Mu, remember, is the population mean, which we have been told is 500. Sigma is the population standard deviation, which we have been told is 100. Again, to get the z-score, we're simply plugging in the formula, which happens to be the sample mean minus the population mean divided by sigma divided by the square root of the number of samples. That gives us our z-score. The p-value is 1 minus whatever the CDF value is for the z that we calculated, i.e. The probability of observing a value that is less than the z standard, like how many values fall below that threshold. We subtract that by 1 to see, well, how many values could have been higher. And then the p-value is 0.03, which comes to 3%. And the z is 1.8. Again, the z-score tells us, our average is 1.8 standard deviations away from the population average, and that the odds of observing a sample that is 1.8 standard deviations away from the population mean are 3.5% or 0.3, as you see there, right? And because our alpha, do they even talk about alpha here? Yeah, so alpha is 0.05, yeah. So because the probability is less than what the alpha level is, we say that the probability that we could have gotten the sample mean by randomly sampling the population is so low, it's lower than the threshold we decided, which is 0.05, that we're going to now conclude that our sample does in fact indicate that, yes, the training had an effect on them and it raised their average score.